Hi. Hi, can you guys hear me?
Yes, I can hear you.
Yeah, we're just waiting for some more people to come. Um, I think. Um, yeah. All right. So, anyways, I'll just introduce myself first before we start. Okay, before that, has everyone got the notes that I sent? I sent one sort of 2 hours ago, but I don't know if you got somebody sent it to you. Um, in any case, you're supposed to have the note that says one dot motion. That's the first one we'll go through. So, uh, this being like a trial class, there are two possible sets of notes that I have, and I kind of want to gauge like how fast the class should be. So, um, yeah, there's like a faster and slower notes. Okay, so, anyways, about myself. So my name is Teddy. I'm from Singapore, and I've been doing math and physics Olympiad, since I was a kid, and then I went to the International Physics Olympiad. I got a gold medal, and now I'm studying math with physics at Cambridge. So I'm doing my master's year now. Yeah. So in Cambridge, I rank um in like top 6 last year. Well, when people say top 6, did it really just mean 6? But okay, anyways. So, is anybody else coming? Okay, so before we start, can I ask, have you guys done any physics kind of thing in school?
Yeah, we just started.
Okay, so the first chapter is always units and measurements, right? I hope.
It's algebra.
Oh, that's math. Wait, what? Okay. Anyways, so uh when we do start a class, the first lesson will be units and measurements, but it is an extraordinarily boring chapter. So we're actually gonna this lesson we're gonna start talking about motion, like actual physics, just to make it a bit more interesting. Okay, so let's open up the one dot motion thing. Um,
I haven't seen the email.
I've not sent an email. Did you get any files? Things that look like this?
No.
Okay, right. How about I will put it on the chat here. You can download it. But really, you can just listen along. It's not a big problem. It's a big file, by the way, and we're not gonna finish all of it today. We're just gonna make a start. Okay. Anyways, so first lesson we're gonna talk about Newton's laws of motion. So this chapter is essentially about boxes and balls moving around, and we make a very simple assumption that you can describe all these things with some numbers. So we basically ignore what's going on inside the object. We just say the object is a point, and we keep track of how it's moving around. So, so there are a bunch of definitions first. So the first word is displacement. So displacement is a vector that tells you how far away an object's current position is from the starting position. So vector means it's like an arrow. It has a magnitude, it has a length, and also a direction. There are some typos with these old double dots, but okay. So whenever there's a rate means change over time. Motion is just a general word for, position changing over time. Now, you may have heard of the words speed and velocity. So speed is a scalar. So scalar means it's just a number. And the speed is the rate at which the object is moving, okay, but it doesn't have a direction. It's just a number, so as to say. And it's actually always, we define it to be always non-negative. So always at least 0. Now, velocity is the same thing as the movement of the object, but it has a direction as well as a magnitude. In 2 dimensions, so left or right, we can write it down as positive or negative or 0. Lastly, there's the word uniform. So uniform means, constant. So uniform motion means constant velocity. So that means it's always moving at the same speed and the same direction. Okay, so is everyone okay so far with these definitions?
Yeah.
Okay.
Yeah.
All right. So again, I want to point out that speed is always positive or 0. But velocity can be positive or negative. So if we define the direction to the right as the positive direction, then this one, the right arrow, will be positive velocity, positive speed. The arrow to the left will be negative velocity. And if you circle back around at a positive speed, you would have in total no velocity, no average velocity. Because you didn't go anywhere if you circle back around. Yeah. Okay. So, right. So we're gonna stick to SI units, or the predecessor of SI units is called MKS units. So position and distance and displacement and height is all in meters, and then velocities are in meters per second. So the average velocity is, what it's quite easy to compute. It's just the average. So it's whatever you moved. So the change in the position divided by the time taken for the change. Okay. But if you think about the first derivative, that is what we call the instantaneous velocity. So yeah, so compared to average velocity, this is like the velocity at an instant. So in general, if you have a so if you just rearrange that, then the displacement being the change in position, is exactly your average velocity times the time, because that is the definition of average velocity. And if you add that to some starting position x0, then that will be x0 plus average speed times time. You can also pronounce it x0, and I pronounce it either way, depending on what's sort of randomly. Okay, now, So what is that? Well, it is the average, the change in the position, the change in position divided by change in time. So what that actually is the slope of this graph against position against time. Okay, so have you guys learned how to find the slope of a graph in math class? You draw this triangle, right? And then you count how many blocks and you divide them. So this is exactly the same thing. Okay, so if you look at this example below of displacement against time, then you can see that in the first bit we have this triangle. So you went 8 meters in 2 seconds, right? So this velocity will be 4 meters per second and plus 4 because it increases, and this bit it didn't go anywhere. The displacement is the same, so the velocity is 0. And in this bit, it decreased by 8 meters in 4 seconds. So the velocity is minus 2 meters per second. Right. So at this point, I want to just point out the difference between distance and displacement. Does anyone have any idea what is the difference? So distance is always increasing. Like if you drive your car around, you always increase in the distance that you drove. So in other words, distance keeps track of this length. Okay. Let's draw it this way. All right. Whereas displacement only keeps track of where you started and where you are now. So this is the displacement. Okay. So distance, it always increases, is a scalar or a number. Okay, and displacement is well, it's a vector really, so it has a magnitude and a direction. Okay, and it can come back around to 0 if your car comes back around to the same point. So I just want to point out that the average velocity and all these that we saw before is the displacement over time. You can also think about things like the average speed, but it becomes a bit less useful because the average speed doesn't actually correspond to anything. Well, it depends on how you want to think about it, but yeah. So speed is for distance and then velocity is for displacement. Right. Everyone happy with this so far? So speed is the change in distance per time and velocity is the change in, well, displacement per time. Okay. Right. Okay. For those of you who just joined, can you see the file that I sent in the chat? So we're on page 3 of that file. Is everyone on this page? Like, do you guys have this stuff? Oh, you can't see the file? I'll share the file again. Okay, yeah, but anyways, you can just listen. So, all right, so some examples. A car travels 1,200 meters in 60 seconds. The average velocity is 20. Just take the distance, sorry, take the displacement and divide it by time. A person walks 320 meters at an average velocity of 1.25 meters per second. How much time did it take? So just take 320 to divide by 1.25 and you get 256. Okay, there's a line break here, so just take note. Right. So now I want to talk about acceleration. So if an object's velocity is increasing, then we say it has positive acceleration. If it is decreasing, then we say it has negative acceleration. So in the graph of velocity against time, if it's going up, then we have positive acceleration. If it's always the same velocity, then we have no acceleration. And if the velocity is going down, then we have negative acceleration. Okay, now this still works because I mean it's a graph, but in the case of negative velocity, increasing the velocity means it gets less negative. So like from -3 goes to -2. That is an increase in the velocity. Right, so the units of acceleration is meters per second square. Okay. And usually we use the letter G for gravity and A for just any acceleration. Right, so again, the same thing, we can say that the acceleration is a change in velocity over some time. So acceleration is, delta of v divided by delta of t. So this is your average acceleration, and this is your instantaneous acceleration. Instantaneous, yeah. Right, so all of these is meters per second divided by seconds, so it'll be meters per second square. And if you're interested, the instantaneous acceleration will be the second derivative of position against time. But at this point, you don't need to do any calculus, so we'll just stick to constant acceleration stuff. So if you have constant acceleration, then the acceleration causes a change in velocity, which means that the change in velocity is acceleration times time, which is, the final velocity minus the initial velocity. So yeah, so now you get this equation, v minus v0 equals to at. Okay. So as I said before, the acceleration is the slope of the velocity against time graph. Okay, so you have a line, you take the triangle for the line, and then you count, if it's a graph paper, you count how many blocks and you divide it. That will be the slope. Now, so we were saying the velocity time graph, and previously we were saying the position time graph, okay? So I want you to look at these 9 graphs, and we're going to try to understand them. Okay, so on the left, we have positive acceleration. So positive acceleration means, yes, velocity is getting faster and faster. So in this example of this graph, okay, we start off with some very small positive velocity, right? Because at the start, the position is increasing a little bit slowly in time, and it gets faster. The position increases faster and faster again. So the position is increasing at an increasing rate. Okay, so that is positive acceleration. On the other hand, we could say another situation is that if the position is decreasing, okay, and the decreasing, well, it gets decreasing slows down, so it gets less less and less negative over time. That's not the right way to put it. The velocity was very negative and then it gets less negative and then less negative again. This is also positive acceleration. Okay, does the first column of the graphs make sense? Also, please tell me if you have not learned this in school before, because I am assuming some math stuff here that you've yeah. Okay. All right. So now okay, so now the middle column, acceleration is 0. So acceleration is 0 means the velocity is always the same, as you can see in this graph. You know, at every point in time, the velocity is the same, which means that since the velocity is the same, the rate at which your position changes is also actually always the same. So your slope triangles are always the same, you know, whether you're increasing in position or decreasing in position. So it's a straight line, okay? So we call this a linear graph, whereas the previous one, we call it a concave up graph, or some people will call it a convex graph. And they will call this one concave. Naming conventions, please stick to the ones you use in school, because that's your school teachers mark your homework, but I don't really mind. Okay, negative acceleration. So negative acceleration is that your velocity gets slower, decreases over time. So let's say your position is at first slowly decreasing, and then it decreases more, so at a faster rate. Like this one is a bit hard to draw. So this slope triangle would look like this, right? Like a tangent line and then draw a triangle. Okay, so yeah, so the position decreases quicker and quicker, or the position was increasing, so the velocity was positive, but getting less and less, so the velocity gets slower. And this kind of graph, this shape, we call it a concave or a concave down shape. All right, very good. Yeah. Okay, anyone has any questions so far? No? All right. Okay, so previously we were talking about the slope of graphs, but you also know that you can also think about the area under the graph. So what does that mean? So, you know, rectangle area is very easy to think of because it's just velocity times time. So if you take in the velocity time graph, if you take the area under the graph, that would be velocity times time, which is the displacement, the change in the position. Now, you can extend this idea to say that in any velocity time graph, the area under the graph is the change in displacement. Okay. Area under the graph is in theory an integral, but we'll always deal with nice enough shapes that you do not need to do the integral. You just need to find the area. Okay. So if you take this example, all right, you know, from 0 to 2 seconds, the velocity graph is this, and you take the area, which is a triangle. You can use your formula to calculate the area of the triangle. And if you do it right, the units should come out correct as well. So the acceleration, yeah, okay, sorry, I didn't miss a line. Yeah, Okay, so this is trying to convince you, right? That if you calculate the area, which is half base times height, so half 2 times 5, half 4 times 10, this one is just base times height. It is, for triangles, it is the same thing as half acceleration times time squared, which we will see later. Anyways, so the area, the units of the area is meters per second times second, which will get you the meters. And that is the unit you're looking for the displacement, right? Okay, just type in okay if you just look at these three graphs and look at the calculation below and type in okay if you agree with them. Right, so you will realize that in math class you spend ages and ages doing algebra, and then because in physics class you can just do it quickly. Right, so now we think about we think about what a constant acceleration means. So let's say we start from no velocity at the start. Okay, so we start from 0 velocity. I think I forgot to write it here. Okay, so we start at rest and then we accelerate, right? We do acceleration times time. So v equals to at is the velocity you get at the end. But that is not actually the average velocity. You can average the velocity just by taking the start and the end and dividing by 2. Now, we also previously said the average velocity is the change in displacement over time. And I hope you can agree that for a triangle graph, well, the average velocity of this bit, it really is just the average of the start and the end, which is the middle, right? Now, of course, if your VT graph looks like that, then the average velocity is not going to be, it's not going to be just the halfway point between the start and the end. But for triangles, everything is so. Okay, so if we start at v0 equals to 0 and accelerate at constant rate, then the average velocity is the average between the start and the end. So half of the end velocity, because the starting is 0, so half v. Okay, so the displacement is the average velocity times time, which is half the final velocity times time, and the final velocity is acceleration times time, so it's half at squared. Okay, so which is exactly what we showed just now with those calculations, that half at squared is actually really the area under a triangle. And if you started with not initial velocity 0, but initial velocity v0, then you will get a v0 t here as well. That's because you're starting. Sorry, I'm get another color. Hang on. That's because your starting velocity is v0. Your ending velocity will be v0 plus at. That means your average velocity is average of that. So v0 plus half at. Multiply that by time will be v0 t plus half at squared. Okay, so that is the general way to find the displacement, under a trapezium. You could, this literally is the trapezium formula, right? Like v0 plus at, then half of top plus bottom times the height. Okay, is everyone with me so far? Okay, very good. Right, now on the next page, there is a magic formula which says v squared minus v0 squared is 2ad. Okay, so let us recap. I actually sometimes like to change these things. Because I wrote these notes a while ago. So why don't you guys grab some paper? And yeah, just grab some blank paper and let's recap what we just said, okay? So we are always assuming a constant acceleration. Okay, and we start. I'm just gonna change some symbols so that you don't memorize the symbols, you just do it as algebra, right? Because if you always see the same symbols, you might be uncomfortable if people give you different symbols. So let's start with velocity u, and we have constant acceleration a, and our starting position is 0. Okay, so what will be our final velocity? What do you think? What do you think will be the final velocity? You can just talk or you can type in the chat. Okay, so v equals to u plus at, right? Because acceleration times time is how much you speed up by, and then you add that to your starting velocity u. Okay. We also learned that the displacement, the amount of this, the displacement, the change in the position, as we discussed previously, will be ut plus half at squared, right? Because it's the average. Sorry, let me just start a new line here. The average velocity, okay, the average velocity is half of u plus v, because it's the half of the start and the end, and it's going to be u plus half at. Then if you take the average velocity and multiply it by the time, you're going to get displacement, right? The average velocity times time. Okay, so this is what we know. All right. I would like you to prove b squared equals to u squared plus 2as. Why don't you give it a try? Okay, very good. So Jeffrey has proved it. Anyone else made any progress? Okay, fine. So yeah, just open it up since you know V is U plus AT. Well, you can do it in many, many ways. You can factorize V squared minus U squared and all this. But anyway, yeah.
I'm done already.
Okay,
So
great. Mm-hmm.
I'll tell you the way how I proved it. So I just squared the I just did like your method similarly.
Right. So yeah, so if V equals U plus AT, you square that, you get U squared plus 2A. Well, let's write it as 2. Should I write it? Yeah, let's write it in alphabetical, I guess. Is that weird? That's a bit weird. Okay. So then you just realize that this thing is 2AS because S is UT plus half AT square. So you can just take out 2A and you get UT plus half AT square. And that literally is U square plus 2AS. Okay, very good. So this equation at this moment to you doesn't really mean anything. It's just a mathematical result. And we can use this result to answer a bunch of questions. Okay, and make it very convenient. So this is sort of the idea of doing physics, which is you start from some very simple equations, right? Like the only idea in this whole thing is just adding A times T, right? But using that, we can deduce more and more complicated equations that do more and more work for you. So that's the point. Okay. In any case, right, so here's V squared minus V0 squared is 2AD, it's the same thing. Now when the acceleration is just G, it's just gravity, we say the object is in free fall. And well, gravity is actually different in different places. And most of the time, I think the questions will ask you to use 10, even though it's like 9.8 something. Okay, so just to mention, there is another level which is called jerk, which is the change in acceleration per time. Jerk is named literally because it feels like a jerk. So imagine, I don't know if you can imagine, but imagine you are on a um yeah, so let's say you have a train, right? And the train tracks was straight and then becomes a turn. So what do you feel if you're sitting on this train? Well, when the train is going straight, you don't really feel anything. And then when it starts, um, while it's turning, what do you feel? Well, you kind of feel that you're being thrown out, you're being pressed against the side of the train. But what do you feel when it enters the turn? Well, when the train enters the turn, everything sort of has a bit of a shake, right? Or a jerk. Everything's like suddenly thrown to the side. I don't know if you have had that experience. Do you guys know what I'm talking about?
Yes.
Yeah. So it's like the moment when you enter the turn, it's not a sustained force, right? It's just like boom, and then you know that you're turning, and then while you're turning, you're like feeling a force pushing you onto the side, but there's a jerk, and that's exactly what it is. It is the change in acceleration because when it's going straight, the acceleration is zero, and when it's turning, there is some acceleration. So the change in acceleration is the jerk. Okay. Anyways, you don't need to know this. It's just a trivia. All right. So we're halfway through the time. So we usually take a break at this point. How do you guys feel about this material? Is it too fast, too slow? No idea what's going on? Or you can message me privately if you want. Um, yeah, I can imagine how it's very new, so um it takes a bit to stomach it, but yeah, if every step that I'm explaining makes sense, then it must be that the whole thing does make sense, even if it's a lot of new stuff and you have to remember it. That's yeah, that's what learning is. So, okay. Yeah, why don't we take a 5 minutes break here, and then when we come back, we'll do some of these we'll ask you to do some of these problems. Okay. All right. Right, hello. I guess back. Okay, sounds like we should. Okay, so in fairness, right? In fairness, there is another set of material that I promised to show. So I'm gonna just show that. For a bit, because I think there are more diagrams here that I mean, it's essentially the same thing. It's just more explanation and less algebra. Okay, so here's the other set of material that I have definitely not sent to you. So this is the standard Singapore like middle school material. Okay, so right, so I'm just gonna spend like, I don't know, 10 minutes to recap by reading this one, and then you can tell me how you like the speed of this material. So distance is the length of a journey for an object. It's measured in meters. Displacement is the change in the position. Okay, so from the start to the end. And distance is scalar and displacement is a vector. For example, if you start from A, you walk left 10 meters and then you walk right 4 meters and you end up at point B, then the displacement is, okay, if we say right is positive, right, then left is -10, and then you plus 4, it will be -6 now. So displacement is -6, but the total distance is 10 plus 4 is 14. Okay, so every step you take, you add the distance, but the displacement, you only care about where you are now. Right, so for example, if you drive along this road, your distance might be 7.7 kilometers, but your displacement is 5.4, and the displacement is an arrow. Okay, if it's 90 degrees, you can use Pythagoras theorem to add up the displacement. But the distance will be 3 plus 4 km. The displacement is 5 km. All right. Speed is distance per unit time. Velocity is displacement per unit time. Okay. For example, when the moon goes around the Earth, it always has, well, assuming that it always has the same speed. Well, nothing really always has the same speed, but assuming it has a constant speed, we say that the velocity changes. Well, the velocity changes because the direction changes, and the velocity is an arrow that keeps track of both the actual speed and the direction. Okay. When you drop a ball, because of gravity, you know, it will gain velocity. The speed and velocity will both increase, and the direction is always the same, which is down, but the velocity will increase. And the formula you'll get is that the final velocity is the initial velocity plus acceleration times time. So v equals to u plus at. The average speed is the total distance over the total time, and the sort of average velocity or the resultant velocity is the total displacement, the overall displacement over the total time. Yeah. Okay, so in this example, they took 10 seconds to do this. So displacement was -6. The velocity will be -6 over 10, so minus 0.6. But the speed is 14 over 10, so 1.4. So the velocity and the speed are actually completely unrelated things, okay, in terms of what numbers you're going to get. Okay, so in this example, if he does this in 30 minutes, then the average speed is 7.7 over 0.5. the average velocity is 5.4 over 0.5. So again, different numbers for the average speed and velocity. Okay, in this example, again, same thing. Yeah. All right. Everyone with me so far? I don't know if you guys prefer the full screen view. Oh, SF. So SF stands for significant figures. So basically, it stands for three numbers here that are important. So the 0 point is not important. But you get three actual numbers over there. It's just like you got a calculator, right? Then how many digits do you stop reading it? Okay. Good. Good. Oh no. Okay, acceleration. So acceleration is the rate of change of velocity. So it's the final minus the initial velocity over the time. Okay. If we say something starts from rest, the initial velocity is 0. And we usually don't read this line. We usually always say that the acceleration is constant. Okay, just read this. We've already said this before, so yeah. All right. I don't know if you guys have a calculator, but can you do this problem? An airplane takes 27.9 seconds to accelerate uniformly from rest to 28.6 meters per second. What's the acceleration? Yeah, so you should just take the two numbers and divide by each other, and you're gonna get 1.0. Well, depends on when you round off. So you can say 1.03 or 1.025 or 1.025089606. Anyways, so 28.6. Well, okay, if we want to be very, very careful, we'll write all of this stuff down. So 28.6 minus 0 divided by 27.9 is 1.025089606, which we'll round it off as 1.03 meters per second square. Okay, all right. Some graph stuff. Yeah. Okay, so again, the relationship between distance and displacement. So the ball starts from A, then it goes to B in 4 seconds, and then it goes to C in 7 seconds. Now, as you can see here in the distance graph, the distance keeps on increasing, and the displacement is like it increases, then does nothing, and then the times are labeled on there. It goes to A, does nothing, and then comes back. So that's why it differs. So distance always increases the displacement. You keep track of the positive and the negative. Okay, so from this kind of graph, you can then, from this kind of graph, you can then deduce the speed. So distance time graph will give you the speed, right? So this thing is 8 divided by 4, which will get you 2, speed of 2 meters per second. This part, the distance is not increasing, so the speed must be 0. And then the next part is, this is 16, this is 4, so if you divide it, you'll get 4. Okay, so the speed graph looks like this, and this. Yeah, and you can do the same for the displacement. Yeah. All right. Describe the motion of this thing. Okay, so why don't you guys tell me? Well, I don't need to. I don't really want any words. I just want you guys to tell me the. Yeah. Okay. So in this case, okay, assuming, right, this is where it gets complicated. Assuming you can only move left or right, so you can only move in a positive or negative way. This is a distance time graph. Can you tell me what the displacement time graph would look like? What would the displacement graph look like? I hope you agree. It can be, there are two possible answers. It is either the same thing or it is the negative of the thing. Right?
Yeah.
Okay. In any case, I hope you agree that it couldn't possibly be like the previous example where it is some positive, then negative, like the direction changes. In this case, the direction must be consistent. Why? Like, why can't it be A, B, and then C like that?
Because the velocity, the speed must like be always like the same sign.
Very good. So we realized that in all of this bit, or at least up to here, in all of this bit, the speed is positive, right? It means that the velocity is never 0, because if the velocity is 0, then the speed is 0. So whereas if you wanted it to do this, well, what this really means is that it turned around, right? If you want something to turn around, there must be a point where it has velocity 0. That's what turning around means, right? Like it stops and then it turns around. If it never stops, it cannot turn around. Right? If the velocity is never 0, the velocity must always be the same sign, either always positive or always negative. Right? Okay. Anyways, assuming this is the graph of displacement as well, then what can we say? We can say A is positive velocity, B is positive velocity, positive acceleration, C is negative acceleration, and D is no velocity, no acceleration. Right? Does that make sense? B is positive velocity, positive acceleration, C is positive velocity, negative acceleration, and D is 0, 0. Yeah? Okay. Right. So, I mean, anything can always be put into an extended discussion. So, right. Okay, all this graph stuff. Okay, so anyways, this is a taster of what this notes is. It's yeah. Okay, let's go back to the other one. This one. Okay. So it's just graph. They're both looking at graphs. So this graph. Right. Can you look at this graph and please find me the velocity between 2 to 4 seconds?
Um, it is moving towards the positive direction, which is moving right.
Okay, what's the velocity?
18 meters per second.
Yeah, so how do we get that? We do, I mean, it's this triangle, right? So you just need to read off the numbers, which is, it went from 18 to 54 in 2 seconds. So the velocity is 18 meters per second. Okay, and there's no acceleration. Yeah. Okay, great. How about between 6 and 7? The velocity is
0.
0. 8 and 10 seconds.
Negative 12.
Yeah. Okay. So I would say the velocity is, so the final velocity is what? 42, this one. And then this one is 66. So if you know, every block is 6 on the graph, right? So final velocity 42 minus the starting velocity 66 over 2 seconds from 8 to 10 is negative 12 meters per second. And also no acceleration. Right. Does that make sense, everybody? Okay, good. Right. Again, you know, this graph 0 to 2, 2 to 4, 6 to 9. Why don't you have a look and then type in the chat your answers. So we're looking for the acceleration now, by the way. Zero to four, 0 to 2, 2 to 4, 6 to 9. Yeah, okay. So the first part is obviously okay, hang on. You're not reading. Wait. So the first part is 6 meters per second velocity and no acceleration. This is a velocity graph. So this number is immediately the velocity. So 6. Okay. From 2 to 4, you get this thing. So you have to find out the change in the velocity. So it went from 2 to 4, it went from 6 to 12, right? So 12 minus 6 divided by 4 minus 2. That's 6 over 2, 3 meters per second square. Sorry, that's the acceleration. Oops. Right. And from 6 to 9, the acceleration will be -4, right? So it went all the way from 12 down to 0. So final is 0, initial is 12, 9 minus 6. So we always, if you want to write the change, right, we always write final minus initial just to, it's just like a consistency thing. Anyways, -4 meters per second square, okay? Right, everyone understand that this starting velocity is 6? Because this is a velocity graph. Right. Okay. Good. Now, here's something more interesting. We have a position graph. I would like you to sketch the velocity graph. So, do you guys know how to draw on the screen, like annotate? Once you figure out what the velocity is, you can annotate and draw it. I'm looking for you to be very, very careful. I don't know if when you annotate it actually draws very well or not. But try to draw it as accurately as you can. Yeah. Right. Yeah, so the first one is 5 because you see that it went from 10 to 35 in 5 seconds. So 20, the change is 25 divided by 5 is 5. Next part is 0. Then the next part is 15 divided by 5, which is 3. And then the next part is it went from 50 to 0. So it's minus 50 divided by 5 will be minus 10 is the velocity. Okay, does that make sense? So, I mean, when you draw these things, right, it doesn't, you can choose to draw this bit or not, the vertical bit. It's up to you. If you use different computer programs, they would, you know, some of them might draw the line, some of them might not. So it's really, it's not a problem, really. So don't worry about it. Okay, good. Right, let me erase. Because mine, like, if I draw, it stays on the screen. So I'll draw. All right, number 4. So this is the very complicated one. So, Carl Lewis did 100 meters in 9.86 seconds, and you record down, you know, the distance against time. Now, you know that he runs in a straight line, so distance is also the displacement against time, and you want to find the velocity as well. Okay, so what I'll do is I will plot so plotting this onto the graph is it doesn't require much effort, so well, it doesn't require much yeah, I'll just plot it for you. So how do you plot it? Well, you say 0 at 0, and then you say 10 at 1.88, 20 at 2.96, which is almost 3, 30 at 3.88, then 4.77, then 5.61, 6.45, 7.29, 8.12, 8.97, 9.86. Okay, now, what you're supposed to do here is you're supposed to draw a very nice line that goes through all of them. Okay. It's really hard to do this on. Okay, something like that. Now, my question to you is, so I'm not going to ask you to draw the velocity very well, but I'm going to ask you, what does the velocity look like? Do you think, okay, the velocity looks like, let me get another color. Do you think it looks like this? This or this? By the way, I don't know what's the actual final velocity, but yeah. Right. Okay, so to answer this question, have you guys run 100 meters before? Can I ask you what is your velocity at the start?
0.
Right, your velocity when you first start must be 0, right? So it must start from 0 and then it reaches, it increases to reach some value at the end, right? So this is what the graph should look like. Okay. Now, so what actually, yeah, so I mean, so now we need to find out. So we know that it basically reaches the final speed. It pretty well, actually, if you try to draw a straight line with your ruler, you can sort of see that, I mean, I would personally say that after 40 meters, this is the final speed. And then before that, the speed is increasing. Right, and I would estimate, I mean, after all, I don't really mind what the answer is, but I would just estimate that, you know, in this green triangle, we're going 100 meters in, let's say 8 seconds. So the final speed is 12.5. Okay, and we basically reached there at about 5 seconds. So we can basically say it's like that. It's very hard to draw graphs, by the way. Yeah, so it kind of looks something like that. Of course, this is not entirely accurate because I am not, you know, I'm not measuring any of the previous stuff, but yeah. Okay. I guess happy with that. So the only point I want to make is that it must start from 0. Okay, that's, yeah. Good. Oh yeah, hang on. Let me ask you, do you think it might actually look like that? So the question is, do you think when it first starts, does it bend upwards or bend downwards? So, I would say, well, the problem is we don't really know, right? Because what you can do is you can put this into a computer, ask it to fit a graph differentiated. But okay, think about it like this. Think about it like this. What if okay, so let's think about it like this. So so a different graph. What if this graph goes like that? So this is, let's say, 0 times 0. And far, far before time 0, the position is almost 0 and tends to 0. And then far, far after time 0, it becomes a straight line, or it tends towards a straight line. Then I hope you agree that in the velocity graph, far, far before time 0, the speed should be 0. And far, far after time 0, the speed should be, let's say, 1. And the sort of only way to connect them is like this. Does that make sense? Does that make sense? So if this is your position, this is your velocity. Like, I'm not saying it this, well, as I hope it intuitively makes sense that it must start with velocity 0 because your slope at the start is 0. Your slope at the end is 1, let's say, and then the only way to connect these two horizontal bits is a double curve line. Right. Okay. Does that make sense? So for this running thing, well, we don't really know where on this double curve line we actually started. We could have started like here or something, and then you actually only get the curving down part. So we don't really know. I would still stick to just being only curving down, because I think when you're running, you accelerate the fastest at the start. I don't think when you run, you will find that you accelerate the fastest somewhere in the middle of your run. I don't know if you have a different experience. Maybe? Okay, anyways, doesn't really matter. Does this kind of make sense? Does this make sense? All right. In any case, plotting graphs is the lifeblood of physicists. Okay, even if you know, you will gain this skill where I show you a function you've never seen before, and you can plot the graph of it without calculating any, well, calculating a minimum number of values, not every point, but like just thinking about some stuff, you can deduce the shape of a graph, which is quite important. Okay, so that's it for today. I hope you enjoyed it. I hope it was not too difficult. That's essentially how it's going to be, which is there is a notes, we talk about the notes, I ask you to do the questions, and then I extend the questions by coming up with some other things. Okay. All right. You can let me know any questions if you have. Or your parents can also ask questions. If not, then thanks for coming and you can go.
Goodbye. Thank you.
All right, thank you.
Bye.